So I will present my paper. It's called Little Data is Often Enough for Distance-Based Outlier Detection. So I think I will start with introducing or motivating the research that we did. So with outlier detection, I'm mostly working in the field of manufacturing, and there is especially in sensor data. And there we have a couple of problems or challenges. So the first problem is that there is basically no labeled data available, meaning that purely supervised learning is infeasible. Then we have large or almost unlimited unlabeled data, meaning that it's very well suited for semi or unsupervised learning. And third, the data is mostly high-dimensional time series data when we're talking about sensor data. And this makes sense to use time series methods for these kinds of problems. So what kind of methods are there for outlier detection in sensor data? And we see this is mostly series data. So basically there are two different kind of approaches. One approach is based on distances, and the other kind of approaches are based on features. So with the distance approaches, you have pretty much to decide which kind of distance function to use or which kind of metric to use. With the feature-based methods, there's a lot more variety. So you can either come up with features on your own or ask experts to come up with features. Or you use something like an autoencoder, which implicitly learns a lower dimensional representation, so it learns the features. And the talk I'm giving now is focused on distance-based methods. And why is that the case? So why do we focus in my research now on distance-based methods? There are two main reasons. The first reason is its ease of use. So it's very much independent of knowledge from a data scientist because there are very little parameters involved. And when you're thinking about implementing an outlier detection system over hundreds of machines, you have it's very difficult to solve the problem individually for each machine. So you have to solve it in a very general setting. The second reason is domain, or the second ease of use is that there is little domain knowledge necessary for distance-based methods because you're making use of the raw input data, basically. So you don't have to find features which sometimes you don't have any experts who can tell you what kind of features you're looking for. So that's also something that makes it a little bit easier to work with distance-based methods. And from the explainability side of things, previously I've shown you that there are mainly two different kind of styles of features. So ones are the features that are crafted by us humans, which are, of course, mostly explainable because we come up with them. But then there are also the features that are come up by a neural network, for which you need post hoc analysis to make sense of the features. So it makes it a little bit difficult to use the approaches in production. And with the distance-based methods, there are, from a paper from Bell and Papantonis, two explainability traits that are inherent to these distance-based methods. One of them is that such distance-based methods are inherently transparent, as it's very easy to understand the procedure, how the model goes through to generate its output. Basically, you only have to know the distance function, and they are explainable in a sense that they extract representative instances from the training dataset to demonstrate how the model operates. And that's the case because pretty much all of the distance-based methods for outlier detection rely on the nearest neighbors. Let me quickly show the difference between global and local outliers that's often very relevant in real-world use cases. So global outliers are outliers in the dataset irrespective of different densities in the dataset. And the local outliers are points in the dataset that might be an outlier in some a part or region of the dataset, but not in another part. So when you see on the top right here, this red point would be totally normal. The density would be totally okay. But on the left here, if you compare it to the other points, it's an outlier. And there are different distance-based methods that deal with this kind of problems. So there are the global methods that compare the density of the outlier points to the density of the overall dataset. And then there are these local methods, for example, this local outlier factor, which compares the density of the point to the density of the nearest neighbors. So in this case, local outlier factor would also decide that this red point is an outlier. Okay, so I have now made a lot of points for distance-based methods, but there, of course, are also problems with them. And what are the problems? What motivated now this research that we did? So the main problem is the computational complexity of nearest neighbor queries, because all of these, or almost all of these techniques depend on the nearest neighbor search, which is very complex. So there are a lot of approximation techniques for distance-based methods, but we seldom know how the prediction result is influenced by approximations. And that's what we focus on in this paper. So what are the concrete research questions that we wanted to ask or to answer? So let me say as motivation again from the beginning, we have almost unlimited unlabeled data available. So we have to somehow find a solution how much data should be used to train a model such that it is fast enough, but still works great. So the first research question is asking, how does random data subsampling influence our detection performance? The second research question asks, how does prototype-based data subsampling influence the detection performance? And the third research question compares the two. So the methodology, we had a lot of data sets. I will show them in the next slide. And we split each of these data sets 50-50, stratified train test split. For the question 1, we randomly subsample the data, the training data, to proportions of it. So for example, 10%, 20%, up to 90%. And for the second research question, we do the same thing, but we don't randomly sample, but we calculate k-means clusters in the same proportions and get the centroids as our prototypes. And there we compare the two main algorithms used in outlier detection. So one is the global algorithm k-nearest neighbors, and one is the local algorithm local outlier factor. And we use hyperparameter optimization in the ranges that are shown here from 1 to, oh, there's a mistake. This should be 10. It's not 100, sorry. And from 15 to 100. And we use the Euclidean distance for all of our investigations. As an evaluation metric, we use the receiver operator characteristic. So here is the list of data sets that we tested or evaluated our approaches. So we took most of the available tabular data sets in outlier detection, and we enriched them by sensor data sets that are currently still proprietary, but we are working on getting these open. So what are the main results now? So there is actually surprisingly little difference when you subsample the data, both randomly, here shown in green, or with prototypes here shown in blue. So when you look at the ROC, AOC scores and the according standard deviation over all the data sets, you see that there is a difference, but it's maybe smaller than you'd expect. At least for us, it was definitely smaller than we'd expect. And if you want to look at the individual dataset results, you can visit the website. So there are all the plots for all the datasets. Okay. So overall, when subsampling to 10% of the data or calculating 10% prototypes, the difference differences between that and calculating using the full data set is according to this slide. And we can see that the local outlier factor is a little bit more sensitive to data reduction compared to KNN. But both KNN and local outlier factor are highly robust against random and prototype-based data sampling. So for the third research question, we asked if there is a difference between random subsampling and using prototypes to reduce the data. And there, the result is that k-means prototypes are better for KNN, statistically significantly better, but not for the local outlier factor. And then I would like to show you a couple of interesting findings. So as I already said, perhaps surprisingly, the variation is pretty similar between using the full dataset and a subsampled version of the dataset, which also, again, shows that the methods are pretty robust against subsampling. And also interesting, if the full dataset is not perfectly described by the maximum of our hyperparameter k, so in this case, k would probably lie above 100, then you would actually get a better result by subsampling, as then the neighbors better describe the dataset. And also, if the number of neighbors is already very low for the full dataset, in this examples here, it's 1, so there's only one neighbor describing the data best, then a subsampling approach leads to declining performance generally. And then I would like to make a little bit of advertisement for the library that we used for this evaluation. So we are developing a Julia library for these kinds of problems, which enables researchers like me to develop such algorithms in very short time and actually implement algorithms that are faster than the current state of the art, for example, with Python. So I invite everyone to have a look at this library. It's working really great. Thank you very much for your time. So I would be open for any questions.
Yeah, Gerd?
Hi, thanks for this this really interesting talk. I also am really enthusiastic to see Julia pop up at this conference. I've been in love with Julia since 0.2, I think. I did have a question about the surprisingness of whether subsampling would change the results, because I guess if you would do subsampling, you would only get different results if you happen to find a cluster of similar outliers. Because otherwise you sample from the big populations mostly, and maybe there might be an outlier there, but then the results wouldn't change that much. I don't know whether that's a question or a remark, but somewhere in between, I think.
Yeah. I mean, generally, we have also observed that the more outliers there are in the dataset, the stabler the prediction results get in regard to subsampling. So if there are 10% outliers, the subsampling is stabler than if there are 1% outliers, which maybe makes sense because they're more equally distributed, probably. Otherwise, I'm not sure if I understood it. So
I'm trying to figure out whether that would answer the question that I have. So you say that if you have fewer outliers, you have less stable models with subsampling.
Yeah. In general, there is higher variation when the proportion of outliers is lower. So that's an inverse relationship.
Yeah, that's an interesting thing. I wouldn't expect that either.
Yeah.
I've got another question, David. How low can you go with respect to the data fraction till you cannot find your outliers accurately anymore? Because we have seen when you go down to 10%, it's approximately the same as if I use 50% or something like that.
I mean, I think the problem with going very low is that the risk, of course, increases that the variance will be very high if you have very little samples. And it also depends on the population you start with. So when we are looking at the data sets, they vary widely in the number of samples they had to start with. So I think it pretty much depends on that.
Sure, but I think it would be interesting to investigate how low can I actually go without decreasing my accuracy, which actually your answer brings me to my next questions. Have you observed any pattern with respect to the groups of data set? For example, are the appropriate data sets drastically different to the ones from the literature, or does your methods is conditional to the number of samples that you actually have? Because I suspect if I only got 50 data points, then I have to use a different